Hi everyone, welcome to my talk on optimizing high-level synthesis in Circuit. Before I start, let me quickly introduce the interdisciplinary team behind this work. I'm Julian and I do research on the compiler side of high-level synthesis and have spent way too much time thinking about modular scheduling in the past. Melanie's day job is to improve lives by optimizing healthcare logistics, but in this case, she's our modeling expert and liaison to the operations research community. Andreas is our man for all low-level synthesis concerns and has started research in that area when I was still in elementary school. And last but not least, Oliver comes from a task scheduling background and is our liaison to the theoretical scheduling community. The position we want to put out for discussion here at the workshop and in our community in general is whether HLS can and should be treated more of an optimization problem in the mathematical sense in the future. So in this talk, I'll outline a bit what that means and what's possible. Of course, following such a methodology is not limited to Circuit in principle and could be applied to other open systems such as Bamboo or XLS. However, the Circuit community has started to build some infrastructure to support optimization-driven HLS there, so this talk references that to make the whole idea a bit more tangible. In the previous talk, Mike and Morten showed us that HLS is lots of engineering work, but Circuit is a great environment for that because its MLIR foundation makes it easy to connect various domain-specific front-ends and to pick the right abstractions for any given lowering flow. Also, Circuit takes care of the surprisingly complicated task of emitting nice Verilog code. But let's move the engineering aspect aside for now and look at what HLS means in terms of algorithms. Also, note that I'm focusing here on static HLS, which means that we start from some kind of untimed data flow graph and want to construct a data path and a controller FSM at compile time. In this context, we have three main concerns. Allocation is about which and how many operators are instantiated in our target data path. Scheduling is about figuring out when the operations in the source graph should be executed in the data path in order to infer the FSM later. And lastly, binding maps operations to operators. In order to make HLS more tractable, both engineering-wise and algorithmically, these concerns are usually split into separate phases. For example, you fix the allocation first and encode it as resource constraints when you are doing the scheduling. However, it is important to realize that what we are dealing here with are intertwined concerns, so they should be considered together for potentially better results. Last summer, Circuit gained an infrastructure for static scheduling. At its core, there's an extensible problem model. An instance of a problem is comprised of operations, operator types, and dependencies, and all these components can be annotated with problem-specific properties. Here on the right, I have an example of a simple acyclic scheduling problem. As you can see, the operations and dependencies form a graph representing the input program, and the operator types represent the modules available for the target data path. A typical input property is the latency of an operator type, and a typical solution property is each operation's start time. Both input and solution properties are validated by the problem model. For example, the start times must ensure that an operation doesn't start before its operands are computed. The infrastructure provides problem definitions and reference schedulers for a couple of problems with or without resource constraints, which are suitable to support the traditional phase separation into allocation, and then scheduling, and then binding. Lastly, to allow the implementation of state-of-the-art approaches, there's also the option to access external solvers, for example for integer linear programming or the satisfiability problem, via Google or RTools. This problem model might sound overly simplistic to you, and I tend to agree, but it actually serves an important purpose. The way I see it, the model helps to clearly communicate which information needs to be provided and what result can be expected. And this is true for both the client and the scheduler, as well as the humans behind it. For example, if you are working on a new flow and have the need to schedule something, you can treat the scheduling infrastructure as a library and just pick a suitable model and a scheduler from the predefined ones. Or say you have a great idea to improve an algorithm for a specific problem. then you have a clean interface to implement your new scheduler against. And of course, you could define new models to cover a specific synthesis aspect you want to improve, and this is what we want to advertise with this talk. To do that, we now present a few successful use cases of optimization-driven HLS in the past. So how do you synthesize hardware with an optimization problem? Well, you have to encode the characteristics of the target microarchitecture you care about as one or more objective functions. We'll see what that means in a bit. My last general remark is that here, scheduling is kind of the base problem, and if required by the objective, respectively, the hardware features we want to model, we include aspects of allocation and binding in the problem. The first and probably most obvious thing we can do in optimization-driven HLS is to compute optimal solutions. Modulus scheduling, for example, has received a lot of attention in this regard. It can be modeled in many different mathematical frameworks, such as integer linear programming or using a SAT solver. This is still a pure scheduling problem, so the hardware aspects we optimize here are concerning the timing behavior. Typical objectives are to maximize the throughput, which means to minimize the initiation interval, and as a secondary objective, to reduce the latency of the data path. These exact approaches, in contrast to heuristic algorithms, are often feared for their worst-case runtimes. However, we believe it pays off to be a bit stubborn here, because in our experience, you can reap the benefits of optimal solutions for small and medium problem sizes just fine. An important quirk of HLS is that we don't have a fixed accelerator architecture, but rather synthesize the microarchitecture while we map a computation to it. How many operators we instantiate is therefore our choice and can be variable in a combined scheduling and allocation problem. The allocation is only constrained by the available low-level resources, such as lookup tables and DSP blocks on an FPGA. In this situation, we have two conflicting objectives. Instantiating more operators results in better throughput, but also causes a higher resource demand. Computing with fewer operators is slower, but saves resources. Which solution is desired is up to the user or some overarching exploration framework. In any case, we are looking to explore a set of Pareto-optimal solutions here, and techniques from multi-criteria optimization can help us to automatically compute these. Another interesting aspect of HLS is that we usually have operator libraries which provide multiple alternatives for the same functionality. The canonical example for this would be the fast versus the slow multiplier module, but also subgraphs or loops for which we have computed a set of Pareto solutions could be handled in the same way. But when should we use which variant? Assuming our objective is to find the smallest implementation of the fastest microarchitecture, an obvious strategy would be to employ the fastest modules on the critical path and slower variants elsewhere. Makes sense, but where is the critical path? That's a scheduling concern, so we should do that in conjunction with the module selection. Overall, we are looking at a problem that combines all three HLS aspects. Still, Circuit's problem model can represent such a problem. In a nutshell, we would replace the fixed association of operations to operator types with a set of candidate operator types and compute the selected type as part of the solution. Solving such a combined problem is hard because we have to make contextual decisions which don't themselves to a greedy strategy, but rather require a global view of the problem. To wrap up and prime the discussion, let me first emphasize that these were past achievements. Do you think that these problems and synthesis objectives still matter for modern domain-specific flows? We find the module selection problem interesting in particular and want to look into tackling it with modern solvers, better formulations, and problem-specific tweaks. To do that, we are looking for host flows where it would make sense to include it in order to derive a representative benchmark set. Also, do you like the idea of optimization-driven HLS and wonder if your next synthesis flow could benefit from a little bit of optimization? Then please reach out. We are very interested in collaborating to model and solve your problem. And that's it. Thanks for watching and enjoy the workshop.